Welcome. Today we'll solve the differential equation. D squared t over d r squared plus 2 over r times dtd r equals 0. This is a second-order differential equation that often appears in physics, particularly in problems involving spherical symmetry. Let's solve this step by step. First, let's make a substitution to simplify our equation. Let's set u equal to dtdr. This means that our second derivative d squared, td, r squared, is equal to du dr. With this substitution, our equation becomes du dr plus 2 over r times u equals 0. Let's rearrange this to standard form. Du dr equals negative 2 over r times u. This is now a separable first-order differential equation. Let's separate the variables. Du over u equals negative 2 over r dr. Now we can integrate both sides. The integral of du over u is the natural log of the absolute value of u, and the integral of negative 2 over r dr is negative 2 times the natural log of r plus a constant c, taking e to the power of both sides. The absolute value of u equals e to the power of negative 2 ln r plus c, which simplifies to u equals plus or minus e to the c over r squared. Remember that u is our substitution for dtdr, so substituting back, dtdr equals a over r squared, where a is our constant of integration. Now we can integrate one more time to get our final solution, integrating both sides. T equals negative a over r plus another constant b. Therefore, the general solution to our original differential equation is t equals negative a over r plus b, where a and b are arbitrary constants. Let's verify this is correct by substituting our solution back into the original equation. First, let's find dtdr. Taking the derivative of our solution with respect to r gives us a over r squared. Next, let's find d squared td r squared. Taking the derivative again gives us negative 2a over r cubed. Substituting these back into our original equation, negative 2a over r cubed plus 2 over r times a over r squared equals 0. Simplifying, negative 2a over r cubed plus 2a over r cubed equals 0, which confirms our solution is correct. This type of differential equation and its solution often appears in physics problems involving spherical symmetry, such as temperature distribution in a spherical shell or gravitational potential around a spherically symmetric mass distribution. The constants a and b would be determined by the specific boundary conditions of the physical problem being solved.